Hi, everybody. We're going to talk about how to solve for a mixed strategy solution. This is our first attempt. And what we're going to use is the idea of equalized expectation, right? If the expected values of all my opponent's strategies are equal, he or she has no incentive to change strategies. Okay, so that's the idea behind equalized expectations, and it will create what John Nash called a saddle point. Now, the first thing that we have to do is you have to check for dominance, all right? And you'll see there is some dominance here, right? If you notice, the bottom row has some large values, but it doesn't dominate the top row. It does, in fact, dominate the row B, okay? So row C dominates row B, rows C dominates rows B. Okay, so we can eliminate that, right? So we just take that out. Why? Because Rose will never play it by the rational play principle, right? So the two ideas of the rational play principle are that Rose is self-interested and and she's perfectly rational, right? So again, and due to those two things, she's never going to play it. So we just eliminate it, and this is called reduction by dominance, okay? And it was um, discussed last time. And now we look at Colin and we say, oh, Colin has a good strategy and B is a good strategy. It turns out that C actually dominates A. If you think about it, remember Colin is trying to minimize here, but B dominates both of them. If we look at this, right, Colin B dominates both Colin A and Colin C. And therefore, that leaves only column B to choose from, right? And of course, Rose, who is maximizing, will choose the 3 and not the 1. So we finish this very clearly. We know that the solution to the game is the equilibrium pair where Rose plays C and Colin plays B. All right, that's a pure strategy solution, or PSS. And we say the game value is 3. Now, of course, we're reporting this zero-sum game value as Rose's value. Clearly, Colin's value is -3. But we'll call the game value 3 because we're using this shorthand notation where we only represent in the matrix the outcomes from Rose's perspective. Okay, and so let's talk about what it means to have a solution to a matrix game, right? And we have to have three things. We have to have the game value. We have to know what Rose's optimal strategy is, and it may be a strategy set. In other words, when we have a mixed strategy solution, right, we're going to end up with a strategy set. And the same thing, we have to know the same thing for Colin. We have to know his optimal strategy or strategy set. So we have this equilibrium pair, a single equilibrium pair, when we have a pure strategy solution. All right. And generally we find those by reducing by dominance. There are other ways, but generally by reducing by dominance. But when we have a mixed strategy solution, we've got a couple of things we have to do, or we can try to do. The problem is if we can't reduce by dominance so that there's only one active strategy, if the players have more than one active strategy, if they both have two active strategies, or they both have three active strategies, then we have to provide a strategy set for the players. We have to not only say which strategies are active, but we have to say what proportion of the time it's optimal to play those strategies, right? So optimal is important too, right? If they're going to be perfectly rational, they're going to have to choose the optimal proportions for the active strategies. Okay, and that's what we'll call a solution to a matrix game. We'll have the game value, we'll have Rose's optimal strategy set, and we'll have Colin's optimal strategy set. Those three things comprise a solution. Okay, getting rid of some stray marks, and we can move on to example 2. Actually, before we move on to example 2, let's jump to example 1 in our notebook. And remember, if I switch to Markdown, my equations display properly, and so I can say the expected value of rows A. I'm sorry, rows B is where we started, right? That rows B is dominated by rows C. Let me get that. So GEQ backslash GEQ gives me the greater than or equal to, right? And so in terms of the expected values, um, it's true. But what we generally say is without expected values. We generally just say it that rows B is, sorry, rows rows C. Let me get this right. Rows C is greater than or equal to rows B. Now, I went ahead and displayed these as, and they're italicized. Why? Because right now the rows, the ROSE symbols, are being treated as variables, right? Which is why I always put in the backslash text, then I've got to put the curly braces around um, the text. But when I do that, I get what I consider to be a much cleaner looking representation. And putting the space inside the text, why? Well, if you want a space between the end of the name rows and the variable capital C, right, you have to put that space inside the text. Otherwise, Python will ignore it. All right, so then that's true. Okay, and what's nice is I can double click in here and I can get a copy of the game. And so I can do my reduction by dominance. This is code, so let me switch to Markdown. Why am I switching? Well, I'm just going to go in here, and here's row B, which is dominated, so I can just delete it and hit Shift Enter, or I can run. Remember, hitting play, the play button here is the same as hitting Shift Enter. They do the same thing. They execute the cell and move to the one below it. So that was a couple of Shift Enters there. All right. Um, and then we have the colon dominance, right? So the same thing happens here, and I'm going to do text. I'm going to do colon space, and here it's B that's dominating. So I'm going to use LEQ for less than or equal, right? And text colon. I need a space in there, and let's do C first. It's interesting in that. Um, B dominates C and C dominates A. There actually is kind of a transitive property thing happening here. But what we do is we list it twice, right? We don't want to list it in that transitive property order because we don't really have a theory for that. So we just list both of them that hey, colon B is colon B dominates colon C and colon B also dominates colon A, right? And so because of that, we can just say, right, that the equilibrium pair is rows C colon B, right? Why? Because rows after the dominance gets rid of those options, her best option is the 3 in the middle, right? So the game value is 3, the equilibrium pair is row C column B, value is 3, and we're done, right? We've provided the 3 pieces of that solution that we're supposed to. Now this one was straightforward because it was a pure strategy solution. We just need Rose's strategy, Rose's single strategy, Colin's single strategy, and the game value. Okay, we're going to jump into a different example now where we have to do some work. Okay, so what are we going to do? First of all, there's no dominance, and you can check for that. But what we're going to do is we're going to calculate Colin's expected values, and you can see them down here. Why? Because our plan, once we have them, is we can use them to create a 2 by 2 linear system with 2 equations and 2 unknowns. And we can solve that. We can actually solve for the components of Colin's or Rose's optimal strategy set. Okay, so that's where we're headed. Let's take a look at these calculations quickly. Okay, so what's going on? We're calculating the expected value of colon A, which are these values here. But we're saying, hey, Rose plays, and we're going to call this V, the percentage of times that Rose plays A. And we're going to call this W, the percentage of times that Rose plays B. And we're going to call this 1 minus v minus w. Sorry, I'm running out of room. But why 1 minus v minus w? Well, the percentage of time she plays her strategies have to add up to 100%. So the third one, if I know the first two, I can solve the third one. I just subtract their sum from 100%, and that's the percentage of time that Rose will play strategy C. So you see me switching from R sub 1, R sub 2, and R sub 3, which are going to be the vector components of the vector R, but I'm switching to V and W and 1 minus V minus W. It's simpler. It's going to simplify the equations that I have to write. Um, and you can pick any variables you want. I tend to use S and T and V and W. Some people use X's and Y's. I don't like using those because we tend to think of those as coordinates, and X tends to be Rose's outcome, and Y tends to be Colin's outcome. So we already have a use for some of these symbols. So I've chosen these, right? And what am I doing? Okay, so for the first outcome for Colin A, the outcome is 6, and the percentage of time that Rose is playing it is V, plus 1 times W, right? The outcome is 1, and the percentage of time that Rose is playing it is W, right? And then the outcome is 0, and it doesn't really matter what this is, since 0 times anything is 0, and we end up with 6v plus W. That's the expected value of column A. And we don't know at the moment what Rose's optimal strategy set is. We're just saying that when we know it, we can calculate Colin's expected value. All right. And jumping back to B, you can see the same thing happens. Right, so for B, we have 3 times V plus 11 times W plus 11 times the 1 minus V minus W, right? So the third one gets kind of awkward when we first write it, but notice the distribution happening, right? So we end up with an 11, and we end up with negative 11V plus the 3V we already have, so it's negative 8V. And then notice we have positive 11V, and when we distribute, we have negative 11V, and they add up to 0. So I end up with the expected value, and there's no W term, right? The W terms have added up to 0. I have a plus 11 minus 11 W, so the W's are gone. All right, and then for C, I have 4 plus V, right, plus 6W, 4V plus 6W plus 8 times 1 minus V minus W. So you see the plus 8 when I distribute. I have 4V minus 8V, so negative 4V. I have 6W minus 8W, so negative 2W. And I hope that's clear how those expected values are coming around. If it's not clear, pause the video here in just a second, right about now, and you can work through those and make sure that those expected values are making sense to you. All right, so what do? We're going to take these three equations here, and we're going to turn them into a linear system, sorry, with two equations and two unknowns. Okay, so um, and it's somewhat your choice here, right? There's three choose two pairs of equations we could make, depending on which one I choose. And I'm really just looking for things that are going to simplify, pretty straightforward. Why? Because I don't want to break out my linear algebra. I want these to be pretty easy linear systems to solve, okay? So what I did here is I set each of the first two equal to the third, and you can see how that happens here. And when I set them equal to each other using the idea of equalized expectations, notice that, right, I can simplify into the normal form. And I'll say the normal form where we have all the all the variable terms on the left and constant terms on the right. That tends to be how we start with linear systems in linear algebra and in basic algebra courses. So we'll represent them that way. Let's look at this. So I have 6V minus 4V. Well, we're moving the 4V over to the other side, so we're adding 4V to both sides. So I end up with 10V. All right, I have a W, and I have to add 2W to both sides to move that to the left. So I end up with 3W. There isn't anything to do to the 8. It's already on the right-hand side, so I leave it alone. I just have an 8 on the right-hand side. So my equation that I'm going to use is 10v plus 3w equals 8. All right, and the same thing happens with the second one. I have negative 8v, but I'm adding 4v to both sides, so I have, wait, I'm sorry, this is going the other way, right? If I add 8v to both sides, I end up with 4v on the right-hand side. And the negative 2v can just stay on the right-hand side, and there it is. But now what I have to do, I have to get the 8 over to the left-hand side. Since I was moving the variable terms over to the right, I've got to move the constant terms over to the left, so I subtract 8 from both sides. 11 minus 8 is 3. So I have 4v minus 2w equals 3. Again, I will urge you to consider the fact that this wasn't the only way to do this. There are 3 choose 2 equals 3 ways to set this up, and you're picking one. Do you always pick the most efficient one? Of course you don't. But you get better at kind of eyeballing it as you're going forward. Some more experience helps you eyeball what the quickest, most efficient way will be. So what are we doing? Well, we're going to solve one of these 2 equations, right? These are 2 equations. We're going to solve one and substitute into the other, okay? And if you look, we are going to solve the top equation and substitute it into the bottom one. So let's just glance at those quickly. Right, so we're going to solve the top. So the 10v plus 3w equals 8 is what we're going to solve. And let me get this right. There seems to be a mistake here. Here's the 10v. We're solving the bottom equation. The 4v minus 2w equals 3, right? The 4v minus 2w, we've added the 2w to both sides. We subtracted 3 from both sides to get to here. So the problem here isn't that I did wrong math, it's that I did the wrong words. We're actually solving the bottom equation, I think, from above. Yes, the 4v minus 2w, and again, what we did on the next slide is we added 2w to both sides, we subtracted 3 from both sides, and that should get us where we're going. Sorry about the mistake in the text of the slide, but this is a correct equation, right? And then I can divide through by 2 to solve for w, and w equals 2v minus 3 halves. Okay, and again, this simplifies pretty well, right? And that's what we're looking for. We're just looking for one that the substitution would be pretty easy for. All right, could I have done it the other way? Absolutely. Absolutely. Okay, so, we substitute in the 10v plus 3w equals 8, so we substitute in for w, and we distribute, and then we're going to take this 4.5, negative 4.5, and add it to both sides. So we're adding a plus 9 halves to both sides. Okay, and 16 halves plus 9 halves is 25 halves. So 16v equals 25 halves, so v equals 25 over 16 times 2, right? So I end up with 25 over 32, if that makes sense. All right, so I've collapsed a little bit of the steps, but I think I've shown enough that you can follow that. So we know that v equals 25 over 32. So what do? Well, we plug it right back in, right? If we know what v is equal to, 25 over 32, we can just plug it right back in and solve for w. So 25 over 32 times 2, so now we have 50 over 32 minus 3 halves. Well, to get a denominator of 32, we have to multiply it by 16. 16 in the numerator and denominator, which you'll notice gives this. So I have 50 30-seconds minus 48 30-seconds, which is 2 30-seconds, which reduces to 1/16. Okay, so now I know V and I know W, so I actually know R1 and R2, so I know what R3 is, right? I take 1, which is 32 minus R1, which is 25 over 32. I've unreduce the 1/16, so I have a common denominator and can do all of this arithmetic in the numerator, right? And 32 minus 27 is 5. In the numerator, the common denominator stays 32, so 5/32. And it turns out that these numbers do add up to 1. We can check that. But let's take a look, right? So basically, now that we've got R1, R2, and R3, we can create this vector. And I like representing the optimal strategy mixture as a vector, right? The vector R um, has as its components the percentage of times that Rose should play her active strategies. Now, if a strategy is not active, what's going to happen is there's going to be a 0 for that component. You play it 0% of the time, okay? But here, all three of our strategies are active, and 25 over 32 plus 2 over 32 plus 5 over 32, that is in fact 32 over 32. So the sum of the R sub i's equals 1, which is what we want, right? They're supposed to be proportions, the proportions of the time that you play your active strategies, okay? So they have to add up to 100%. Okay, so those are Rose's optimal strategy mixtures. So that's one of the three things we need. We still need Collins' um, optimal strategy mixture, and for that, we actually solve for Rose's expected values. Why? Well, because they're going to be based on, oh, Colin plays strategy A S percentage of the time, and he plays strategy B T percentage of the time, and he plays strategy C 1 minus S minus T percentage of the time. So I can take those values and create the expected value of Rose A. Well, Rose A is 6S plus 3T plus 4 times 1 minus S minus T. So I have 6S minus 4S, which is 2S. I have 3S minus 3T minus 4T, which is negative T, and I have a plus 4. All right, so just the same as before, except for now we're going across the rows. Okay, getting rid of the stray marks. And we do it for rows strategy B. That's 1 times S plus 11T plus 6 times 1 minus S minus T, right? So I have S minus 6S, which is negative 5S. I have 11T minus 6T, which is 5T, and I have the 6. Okay, and for row C, I have a 0 here, so 0S plus 11T plus 8 times 1 minus S minus T. So I have a negative 8S to add to the 0. So I have negative 8S. I have negative 8T to add to the 11T, which is positive 3T, and then I have the 8. Okay, so those are correct. And so what are we going to do? We're going to set the first equation equal to the second and the second equation equal to the third. Again, I urge you to consider if there would be a better way to do it. I'm not swearing this is the best way. I'm saying there are three different ways to do it, and I picked one, the one that I thought was best. So what have we done? As we said, we took equation 1, set it equal to equation 2, set equation 2 equal to equation 3. All right, or expected value. I'm sorry, it's not equation, they're expressions. But the expression for rows A is equal to the expression for rows B. The expression for rows B is set equal to the expression for rows C. And the simplification, does it make sense? Well, what have we done? We move the 5s over to the left and get positive 7s. We also have moved the 5t over to the left, but that requires subtracting 5t from both sides, so I have minus 6t, and now I want to move the 4 over, so I'm subtracting 4 from both sides, so I have 2. Okay, in the second equation, what am I doing? I'm moving the negative s over, so it's positive 8s minus 5s is 3s. Same thing, I'm moving the 3t over, so I'm subtracting 3t from both sides, so 5t minus 3t is 2t. And now I've got to move the 6 over to the right-hand side. Well, that requires adding -6 to both sides, and 8 minus 6 is 2. All right, so that it takes some work to get it set up, but once we do, it's pretty straightforward. 7s minus 6t equals 2. 3s plus 2t equals 2. Okay, and what are we going to do? Well, we're going to solve for t in the second equation. So what do we have to do? Well, the first thing we do is we subtract 3s from both sides, and then we're going to divide through by 2, right? When I divide through by 2, you'll see some real nice simplification happens. And I'm going to have t equals 1 minus 3 halves s, but we'll show that on the next slide. You'll see that as we go forward, right? T equals 1 minus 3 halves s. Then I plug that into the other equation. So 7s minus 6 times t, and this is where I do the substitution, equals 2. So I have 7s minus 6 minus 9s. Let's look at that, right? Because the 6 cancels with the 2. So I have 3 times 3 in the numerator, which gives me 9s, but the denominator is 1, so it doesn't have to be shown, right? So it does actually reduce to 9s. It does take a second. When I first looked at that and wrote it that way, I was like, ooh, that's wrong. It does feel wrong, but if you think about the canceling numerator denominator that's happening on that distribution, you go, oh, I see. I see. So we have 7 s's and 9 s's, which is 16 s's. We add 6 to both sides and get 8. So divide through by 6, we have 8/16 or 1/2. Yay, this is going well, and this is going a little easier, right? We didn't start off with a 25, 30 seconds, right? We started off with a nicer fraction, and then we just plug in, right? So s is equal to a half, and we multiply it by the 3 halves, and we get the 3/4. 1 minus 3/4 is 1/4, so we know that s equals a half, and t equals 1/4. Well, we're making a lot of progress in a real hurry, and I will warn you, when you see one that works out that simply, like we just did, you think, oh, they should all be that easy. They're not all that easy. Sometimes you're stuck with doing some arithmetic, some algebra. As a now retired professor, but who worked at University of North Georgia for a long time, Dr. Woods used to say, sometimes you just have to beat it with the algebra stick. And that's true. This one we didn't have to beat it with the algebra stick very much, and it surrendered the answers to us rather easily. Sometimes, though, we have to work a little harder. So what do we have? Um, well, I hope you can see that 1/4 plus 1/2 is 3/4, and 1 minus 3/4 is 1/4. So I didn't really show that extremely detailed, but C3 is 1/4. So I can just put in 1/2, 1/4, 1/4. That is Collins' optimal strategy mixture. Vector C is Collins' optimal strategy mixture. Now, we've got almost everything we need. We've got Rose's optimal strategy stricter. Use your words properly. We have Rose's optimal strategy mixture, that's vector R. We have Collins' optimal strategy mixture, that's vector C. What we need right now is the value of the game. And how do I find the value of the game when I'm doing equalized expectations? Well, I have all of these expected values up here, right? And I know what the optimal strategy mixtures are now, right? So I go back and I get one of the expected values. Here's the one for Rose, but I know what S and T are equal to. So I plug in to the expected value S and T. So S is a half, plug it in. 2 times a half is 1. T is equal to 1/4, so plug it in. So 1 minus 1/4 plus 4. So 1 minus 1/4 is 3/4 plus 4 is 4.75. Okay, so that's the value. Now, we can check our work. This is one of the nice times where you just say, hey, we'll just pick another one. Well, hey, let's just pick Rose B and negative 5s plus 5t. I can substitute in the 1/2 and the 1/4, and you notice that is, and I'm getting a common denominator too. So this is negative 5 halves, but I want a common denominator of 4. So negative 5 halves becomes negative 10/4 plus 5/4 plus 6. Well, negative 10 fourths plus 5 fourths is 5 fourths, but it's negative, so 6 minus 5 fourths is 4.75. And it's nice that it's checked out, right? And I will say on a test, if I want to be exceedingly accurate, and I want all the points, right? I'll check two for Rose and one for Colin, or two for Colin and one for Rose. Why? Well, they're different linear systems, right? So if I check one expected value for each player at minimum, right, and they match, I feel like that's helping triangulate on both linear systems matching. So check at least two, maybe three of the expected values to verify your solutions here. And And here's the full game solution, right? So here's the game on the left. You see it. The value of the game is 4.75. Again, that's Rose's value, not Colin's, because we've represented the game, right, in the simplified zero-sum game uh, formation, right? And we not only have the value of the game, we have Rose's optimal strategy mixture, and we have Colin's optimal strategy mixture, all right? Okay, so let's jump into our notebook, and you might have to pause the video a couple of times to get all of these equations. But first of all, if I'm in Markdown, what I'm going to do, I'm going to show you that we're working in begin align, okay? But in Python, that'll mean starting with a double asterisk, and I'm going to do an end align y. I mean a double dollar sign, right? I'm going to do an end align y. I'm going to close it, right? I'm going to put my opening and my closing, and what happens is every single equation that I want aligned can be put in here, right? And so what I'm going to do, I'm going to do expected value of, and I'm doing this one from the slide, right? I'm doing expected value of Colin based on Rose's optimal strategy mixture R sub 1, R sub 2, and R sub 3. We don't know R sub 1 and R sub 2 and R sub 3 yet, but we plan to. Okay, so the text I'm going to put in is colon space A, close parentheses. I'm going to put in my alignment character and my equal sign, and then I'm going to do what? I'm going to finish the line. Why? Because these are very similar, and I'm just going to change one symbol. So I have expected value for colon A, B, and C. And if you hit play or hit shift enter, you'll see, okay, we have the expected values coming up. The expected value for colon, remember, is 6v plus w plus 4 times 1 minus v minus w. And what am I going to do? I am going to copy paste these. Why? Well, because I need the v, right? Because for colon B, right, it's 3v plus 11w plus 6. And then for C, it's 4v plus 6w plus 8. All right, we're getting there. We're getting there. Okay, and the last thing we'll do is we'll do the equal sign and we'll simplify, right? So 6v minus 4v, so I have 2v, right? I have w minus 4w, which is negative 3w, so 2v minus 3w plus, oops, sorry, plus 4. And let's just look, and you'll see that that is in fact what we calculated. Wait, what? Let me take a look at this. 6v minus 4v is 2v. W minus 4w is minus 3w. And then plus 4. And what I did was I'm grabbing the 4 from here, not the 0 from here. That's the screw up, okay? So sorry about that. And that is, in fact, why it didn't work out right, because we have a 0 here. All right, that makes sense. Now I do 6v plus w and nothing, right? There's just nothing else because the 0 has been multiplied and um, sorry, 6v plus w, which matches what we had here. Sorry about that. And okay, so we're going to simplify again. And let's see, we have 3v plus 11w plus, this one's going to be, I have a 6 there. Again, I started grabbing these off of the rows like I was doing the rows. Sorry about that. So we have 3v minus 11v, which is negative 8v, and for w we have 11w minus 11w, which is 0 plus 11, so we have negative 8v plus 11, which is exactly what we get here. And sorry, you're seeing my recording software screen pop up every now and again. Let me just switch this way. And the last equation that we're going to get here is going to be what? We're going to have 4v minus 8v, so that's going to be negative 4v. And we're going to have 6w minus 8w, which is negative 2w, w. And then we're going to have plus 8. And again, that's exactly what we get for the expected value of column C. That's what we got on our slide, and cha-ching. Okay. Now, I'm not going to go through how to do all of the algebra because I showed it on the slide. And again, I did a bunch of lines on the slide. I did it like this and grouped steps together. And you can do so and also include whatever text you want to help you remind yourself of what's going on. All right, so now would be a good time to pause the video and do the work either by hand and then put it in the notebook, or if you're taking notes, externally from the notebook, that's fine too. But we solved the game and we're ready to move on to example 3. Okay, and I'm sorry, no, we're not. We did the expected values for column C. We're ready to move on to Rose's expected value in example 2. My bad. Okay, so just making sure that these are right. What are we doing? We're going across the row. 6s plus 3t plus 4 times 1 minus s minus t. And you see that written here. And that simplifies to 6s minus 4s, which is positive 2s. And 3t minus 4t, which is negative t plus 4. All right, and in the second row, I have 1s plus 11t plus 6 minus s minus t. So I have s minus 6t, which is negative 5s, and I have 11 minus 6t, which is 5t plus 6. And here I get the 0, so it's 11t plus 8. But I'm subtracting, right? So I have negative 8s, and then I have 11t minus 8t, which is 3t, and then I have 8. And again, I'm going to use these 3 expected value expressions to create a 2 by 2 linear system, 2 equations, 2 unknowns. And again, there are 3 different ways to do this. I chose to set the first expression equal to the second and the second equal to the third. And you can see that right here, right, where 2s minus t plus 4 is set equal to negative 5s plus 5t plus 6. And then the second equation is set equal to the third, the negative 8s plus 3t plus 8. All right, and then we simplify. And again, there's no proper way. Move all the variables to the left, move all the constants to the right. No, that we're gonna simplify whatever way makes sense. The way that makes sense here is add 5s to both sides and get the 7s. Then we're going to subtract 5t from both sides and get the negative 6t. But then we have to take the 4 and move it over. So we're going to subtract 4 from both sides to get the 2. Same thing's going to happen here. We're going to add 8s to both sides and get positive 3s. We're going to subtract 3t from both sides and get positive 2t, but then that means the 6 has to go over the other direction. So subtracting 6 from both sides leads to a 2 on the right-hand side. So that's how that works. Um, you hope that it's easy. It's not hard algebra, but again, we're looking ahead to try to see the most simplified version of the three that we could try. And to solve for t in the second equation, I subtract 3s from both sides and I divide through by 2. Okay, and so I have t equals 1 minus 3s, and I substitute that in. So 7s minus 6t equals 2 is the equation I'm substituting into. So I end up with the 7s and the 9s adding together to be 16s. If I add 6 to both sides, I have an 8 on the other side, and yay, it simplifies to 1/2. All right, so I have um, s equals 1/2, but then I can plug that back into what t is equal to, right, and find that t is equal to 1/4. This is pretty straightforward arithmetic and algebra right here, so I'm not going to go over it in detail. But I'm going to note that, hey, once I know that s is a half and t is a fourth, 1/2 plus 1/4 plus 1/4 equals 1. So we're able to solve for the third component of the vector c without, I didn't even put it in. It's just really straightforward arithmetic. Okay, so we have Collins strategy mixture. And to solve for the value of the game, what are we doing? We're taking any of Rose's expected values, right? And we're plugging in. And we get 4.75. All right. And we see the final solution there. Good. So, and you can see, we'll jump into example 3 in just a second. All right. So the first thing we're doing now, we're switching up our order, expected value of rows A. So I have 12s plus 2t plus 2 times 1 minus s minus t, which simplifies to 10s plus 2. Then we have negative 2s plus negative 3t plus 12 times 1 minus s minus t. So I end up with, when I do the subtractions, negative 14s minus 14 minus 15t plus 12, and negative 2s plus 5t equals 2. Okay. Again, you may need to pause the video to catch up on the arithmetic and algebra here in example 3. But the linear system we're creating, the ones I chose, I set the first and second equations equal to the third. Okay, and you see that right here, the first equation, and there's the second equation, and here's the third equation. It's identical in both linear systems. So now I'm simplifying, and you'll notice that I start by adding 2s to both sides in the top equation and get 12s. And then I want to subtract 5t from both sides, and then I want to subtract 2 from both sides, which gives me a 0 over here, which is actually kind of helpful, right? Because it's going to make solving for s or t in this equation pretty straightforward, which will come up in just a minute. Right, and then with 14s, what am I doing? I'm moving that one over. I'm adding 14s to both sides so that I have a positive 12s. I'm adding 15t to both sides, but t was already positive. The t term was already positive over here, so I have plus 20t equals 10. Where's the 10? Well, when I subtract 2 from both sides to get the 2 over to the left, I get 12 minus 10, 12 minus 2, which is 10. All right, so that's pretty straightforward. And then what can I do? I can solve for t. I add 5t to both sides, and I get a real nice equation, right? 12s equals 5t, so s equals 5/12t, which I can plug into the second equation for s. All right, and here, this is nice. The 12s cancel, so I just have 5t. 5t plus 20t equals 10, or 25t equals 10. Dividing through by 25, and then I can get to a common denominator. It's 10 over 25, or 2/5. Then I can plug the 2/5 back in and get, in this equation, right, 12s plus 20 times 2/5. Okay, well, what's the 2/5? Well, the 20 is going to cancel with the 5. The 5 is a 1, the 20 is a 4. 4 times 2 is 8. So this is just 12s plus 8 equals 10. Subtract 8 from both sides, divide through by 12. So I end up with a 2 in the numerator, a 12 in the denominator, which reduces to 1/6. So I have t equals 2/5, I have s equals 1/6, and now I have enough information to be able to solve for the third one, right? Since s plus t plus c3 equals 1, right, I can substitute in. I have 12/30ths. I'm taking that 2/5 and I am converting to a denominator of 30. I'm taking 1/6 and, converting to that common denominator. So I have 17/30ths. That's the sum of s and t. So 1 minus 17/30ths is 13/30ths. And you can see that we have Collins' optimal strategy mixture here. Okay, solving for Rose's strategy mixture. Again, we're going to do across the top row is going to be 12v plus 2w plus 2 times 1 minus v minus w. And I'm sorry, we're solving for Rose's strategy mixture, so we're doing Collins' expected value. So that's 12v minus 2w plus 0, right? So 12v minus 2w. And then for column B, we're doing 2v minus 3w plus 7 times 1 minus v minus w, which simplifies to minus 5v minus 10w plus 7, right? And then the last one is 2v plus 12w plus 2 times 1 minus v minus w, which simplifies to 10w plus 2. All right, so far so good. And we set the second expression equal to both the first expression and the third expression. Okay, and you can see that the simplification very quickly leads to 12v minus 12w equals 2, and 17v plus 8w equals 7. Okay, so we solve the first equation and substitute in the second. So with 12v minus 12w equals 2, we subtract 12w from both sides and divide through by 12. So I have 1/6 when I divide the 2 by the 12, right? And when I divide 12w by 12, I just have w. The 12s cancel. So then I substitute in my w plus 1/6. That simplifies. So 25w equals 7 minus 17/6. Where is the 25/6 coming from? Well, if you get a common denominator, 7 is equal to 42/6, and 42 minus 17 is 25. So this is actually just doing the arithmetic here. Notice then we have numerator canceling with the denominator, right? So w equals 1/6. All right, and jumping forward, okay, so we can solve for v now. We substitute in the 1/6 there, so 12v. Well, this is going to be real easy because there's going to be some cancellation. So 12v minus 2 equals 2. Add 2 to both sides to get 4 on the right-hand side. And then v equals 1/3. So we're doing well. And then to get, since we have v and w equal 1/3 and 1/6, right, we know that the last one has to be 1/2. That's pretty straightforward arithmetic. So this one simplified nicely. And we have Rose's optimal strategy mixture. 1/3 is the first component, 1/6 for strategy B, 1/2 of the time she should play strategy C. Okay, and when we put it all together, we can double check based on expected value to get the game value. And so when we substitute in, we get minus 5 times 1/3 and minus 10 times 1/6. Okay, well, what's going on there? We're going to jump to negative 10/6 minus 10/6, so that's minus 26 plus 7, which is 42 over 6. 42 over 6 minus 20 over 6 is 22 over 6, which reduces to 11/3. It also checks out if we do Rose's value, we get 11/3. So again, double checking to make sure that we get the proper game value. And then to summarize, right, the game value according to Rose, from Rose's perspective, is 11/3 or 3.67. And the optimal strategy mixtures are the ones we found. Okay, so what are the key points? The key points are there are three pieces to a solution in game theory. I have to know the value, I have to know the optimal strategy mixture for Rose, and I have to know the optimal strategy mixture for Colin. Once I have those three things, I have a solution to the game. So, in the case where we don't have a pure strategy solution and we're stuck trying to solve a game with mixed strategy solutions where more than one strategy for Colin is active, where more than one strategy for Rose is active, I can use equalized expectations. Are there other ways to solve a game theory matrix game? Absolutely. But the way that's the most straightforward that we want to present in this class is the process of equalized expectations.